A number of my viewers have expressed disappointment and a measure of irritation with me over the low grades I have bestowed upon the various science fiction planets that have been analyzed throughout this series. As such, I have received several requests to show what a perfect score S-grade fictional planet would actually look like. Unfortunately, I've yet to encounter one in the wild, so I'm going to have to build one. To start off, I'm going to define the planet's surface gravity as being a bit lower than Earth's at about 0.96 g. I also want this to be a terrestrial planet with a similar structure to that of Earth and a metallic core large enough to generate a geomagnetic field capable of protecting its atmosphere. This requires that its mean density be somewhere between 4,500 and 6,000 kilograms per cubic meter. I'm going to set it equal to 5,217, which is about 5% lower than Earth's mean density. With these values and a little bit of math, I can now calculate the planet's mean radius to be approximately 1.0131 Earth radii, and its mass to be 0.984 Earth masses. There are a lot more details that I could add to the planet's structure, but I don't want to overcomplicate it. My goal here is to build the simplest planet that could receive a good grade. So to do that, I'm only going to define the bare minimum parameters necessary. Before I go any further with the planet, I need to turn aside and build the star that it orbits. I'm going to make it a main sequence star similar to our Sun, which means it will be in the G spectral type. But just for fun, I'm going to roll a 10-sided die and let that determine what its subtype will be. So it's going to be a G4 yellow dwarf star. For the sake of brevity and simplicity, I'm going to use the standard values for the star's mass and luminosity without any modification. It's kind of boring from a creative perspective, but it will save us a bit of math. That gives the star a mass 98% that of Sol and a luminosity 91% as bright. Now that I have these values, I can use the star's luminosity to calculate how far away the planet should orbit from it. I'm going to have the planet receive a similar amount of energy to that which Earth receives from the Sun, about 1,361 watts per square meter. So I'm going to set this planet's stellar irradiance value a little under that at 1,304. A little more math, and I can calculate the planet's average orbital distance to be approximately 0.9746 astronomical units, and its orbital period to be 354.11 days, or 432.94 local days, given the planet's 19.63-hour synodic rotation period. Moving on to the planet's climate, I'm going to give it an oceanic coverage of approximately 81% and an atmospheric composition of 82% nitrogen and 16% oxygen at a mean surface pressure of 112 kilopascals and an average surface temperature of 13 degrees Celsius. Its atmosphere is likely breathable to humans, but not comfortably so. Lastly, I'm going to give the planet a satellite. But instead of giving it a spherical major moon, as one might expect, I'm going to do something rarely seen in science fiction planets and give it a single minor moon. Since this moon's surface gravity is low and narratively unimportant, I'm going to use slightly different math than I did earlier that will allow me to arbitrarily define the size of its asymmetric shape and use a mean density approximating solid rock to calculate its mass. This gives the moon an average size of 25 by 21 by 33 kilometers and a paltry mass of 2.2 times 10 to the 17 kilograms. I can choose whatever I want for its orbital distance so long as it is above the Roche limit and below the Hill radius. An average distance of 0.43 lunar distances is well within those bounds and so should be fine. I will then use Kepler's third law of planetary motion to calculate the moon's orbital period to be approximately 7.85 days. To make it truly realistic, I should also give the moon an inclination and eccentricity. However, as much as I like to see these values, I never fault a science fiction planet for not including them, so I will forego adding them here as well in order to keep with my minimalist theme. That just leaves the planet's name. Since this planet exists only to serve as an example, there is no real need to give it anything more than a catalog name. But that's no fun. So instead, I think I'm going to be snarky and dub the planet Sostos. So how does the planet Sostos measure up scientifically? A lot of science fiction creators mess up their planet's geophysical realism by assigning arbitrary values to its size and surface gravity, and unknowingly defining the planet's mass and mean density in the process. This can result in their planet having an unrealistically low or impossibly high mean density. Though the range of realistic mean densities is, fortunately, broad enough for many sci-fi planets to end up inadvertently accurate despite their haphazard construction. But Sostos was built using a realistic mean density as the foundation to calculate its mass and size, thereby guaranteeing that it is physically accurate. Most science fiction planets get a 0 for their orbital realism because their creators, for whatever reason, choose not to offer this information, though they do tend to provide the orbital period when they arbitrarily define the length of their planet's year. On its own, this value is meaningless. However, if they have defined information about the planet's parent star, then this value can potentially reveal that the planet orbits too close or too far from the star to be habitable. Sostos had its orbital distance defined by the star's luminosity and its orbital period calculated from this and the star's mass, making its orbit completely accurate. Climate modeling is one of the most difficult aspects of planetary science. Because of this, I try to give science fiction planets the benefit of the doubt and award them the point in this criterion as long as the data they've given at least vaguely matches the way the planet is depicted, and they haven't done something extreme or ridiculous like have the planet excessively hot or cold, try to have a uniform temperature and weather conditions across the planet's entire surface, or stuff its atmosphere full of rare and unlikely gases. I've endeavored to keep Sostos' atmosphere and climate similar to Earth's and well within the bounds of believability, so I'm going to give myself the same benefit of the doubt. Many science fiction planets fail to pass this criterion due to their creators' insistence on the planet possessing multiple spherical moons. I have gone on about this at length in numerous past videos, so I won't do so again here, but suffice to say, this isn't realistic. A terrestrial planet can have a single major moon, it can have multiple minor moons, it can have both, and, as is most likely the case, it can have neither. Sostos errs on the fairly likely end of this range with a single minor moon, and since it includes the basic level of geophysical and orbital data, it gets awarded the point. Most science fiction creators completely neglect the star that their planet orbits, considering it nothing more than stage lighting. Some try to put their planets around real stars, which itself is a good idea, but often they place them around stars with notable names. These tend to be among the brightest stars in the sky, often making them too luminous and short-lived to support habitable planets. Sostos, however, orbits a star in the low mass range that is capable of remaining stable for more than 10 billion years, making it very suitable for habitability. And since the star's mass and luminosity have been defined, the planet's climate and orbital characteristics have a realistic foundation. With a total of 5 points, the planet Sostos from Alien Planetology receives an S grade. I am frequently accused of being overly critical in my analyses of science fiction planets and of nitpicking in order to find their flaws. But the reality is quite the opposite. I am very forgiving of a planet's shortcomings and try to be generous when awarding points. If a stated quality of a sci-fi planet is even remotely plausible, then I tend to give it the point. It's just that most people don't realize how poorly built most science fiction planets actually are. But hopefully now you know what a realistic fictional planet looks like, and you have an idea as to why so many planets from popular science fiction fail to receive a high grade. If you would like to learn how to build realistic planetary systems that could also receive a perfect grade, stay tuned to my channel as I have a series in development that is designed to teach just that. So subscribe if you haven't already so you don't miss the first of those videos coming soon. Until then, my course is set to leave realism behind and return to the comical cosmos of science fiction planets. I hope to see you there.